Great. All right, I'm happy to get back to regular meetings. So this will be the last meeting, session 49 of chapter 5. So we're wrapping up integrals, and the next chapter will be, I think, more interesting applications of integration. So the plan for today is, I initially called this part a preview. I've been including these previews at the beginning, but then I realized that if you're a chemist, you will never actually learn these things. So it's not really a preview, it's more just scripture. It's to convince you that there is much more to mathematics beyond calculus, and I'm going to tell you some things from beyond calculus in the first part. So that's scripture. Then, since it's been a while since we had a sort of lecture style session, I want to summarize all the integration techniques we did in a rapid summary with some examples, although maybe you don't need it since you did so well on the integration B stuff. Then one lingering thing I never told you was the general case of partial fractions when there's higher degree. So I'll tell you that and just quickly sketch a proof. And then this is really starting the applications of integration. So this is starting chapter 6. Chapter 6 is really all about showing you that although we came up with this idea of an integral for a very specific problem, the area under a curve, it turns out that the integral is much more general. It's not just areas under curves. It's actually one of the most central ubiquitous objects in mathematics. The integral is really just the correct way to think about addition, summing things up. So the integral is just a sum of quantities which are changing. So it's a sum with change. And we'll make that much more precise by seeing many more examples. But the first one will be today, going up to volumes. So that is the plan. And as usual, just shout out and interrupt me if anything catches your attention or if you have interesting comments or questions. But
I had one less than 5 seconds ago and I forgot it.
Oh, was it about this integration equals summing thing, or?
Oh yeah, it was something along the lines of, you say that that a lot of math is based off the integral. Does that mean? And you're talking about addition, and everything, all forms of math are based off of addition.
Well, I don't know if all forms of math are based off of addition.
I mean, literally addition, subtraction. I'm trying to say all arithmetic.
Yeah, arithmetic is certainly addition, subtraction, multiplication, division. That's not all of mathematics, certainly. But yeah, I was trying to argue that integration is the continuous generalization of addition, right? Yeah, so I try not to think.
Okay.
I mean, even though we learn arithmetic first, I try not to think of mathematics as really being about arithmetic. Like, just, I mean, plus, minus, times, and divide is not, really all of mathematics. It's not even the starting point for mathematics. It's just what we learned in preschool. Good. Other thoughts?
Nope.
Maybe I should keep a counter, and every time you shout out and interrupt me, I should just increment it and then pay you like $1 each time or something. Like, I need to incent.
Oh god.
I want more interruptions.
That would be counterproductive.
How it pun on counter.
Oh come on.
All right, first the scripture. So I want to first just.
I was expecting Feynman.
Yeah. So usually it is Feynman when I say scripture. Good. So when we introduced this notation of putting a dx at the end of an integral, I told you at the beginning that this is just a meaningless placeholder to remind us of what the dummy variable is, right? The dummy variable of integration here is x, just in the same way that if you put a sum from I equals 0 to n, this symbol is just reminding us that I is the dummy variable. So in the story that we're telling, in the form of calculus we're developing here, that is true. Dx is totally meaningless. It's a placeholder. But then we did U substitution, and I told you that, okay, there's this theorem, the substitution rule, that tells you that integral of f of u du is the same as integral of f of g of x, g prime of x dx. And then I said, here's a useful mnemonic for remembering that formula. If you replace the function g of x with u inside the f here, and then you replace g prime of x dx with du the way that I've shown in the underbrace here, then that mnemonic will always give you the right answer for the substitution rule. So, of course, I mean, you were right to be skeptical about this, and we went through some proofs that this will always work. But still at this level, du and dx don't mean anything. They're just placeholders, and this U substitution is just an abusive notation that gives you the right answer. It's a way of remembering the answer. But, okay, so you might say, if it's so meaningless, then why does it seem to be really useful and have this interpretation in terms of U sub? So the first clue that there might be more to it is to try to think of it geometrically. So what is U substitution geometrically? Suppose we want to find this area, so this is like the integral from, I don't know, 0 to 3/2 in this graph. I'm going from 0 to about 1.5. So this is the integral of 2x e to the x squared dx. Here's the placeholder. So in the top plot, this is just that curve in x versus f of x space. So this is the plot x versus f of x. And I'm just showing the curve, and then the area that we would want is, of course, just this shaded region down here. But of course, when you compute this integral, you know, by looking at this, you say, oh, there's an x squared up here, there's a 2x down here. So if I do u equals x squared, then the du eats this 2x, and it's much easier because then it's an integral of e to the u. What does that mean pictorially? Well, if we re-express this region in a plot of u versus f of u, so now this bottom plot has u on the horizontal axis and f of u on the vertical axis, the graph looks different because now this thing is 2 square root of u e to the u. That's what you get just by plugging in the integrand here. So the graph looks different, and therefore the area under this graph would be different than the area under this graph, naively. But we can make the two areas agree if we correct for the difference between these two graphs by mapping old intervals in dx to new intervals in du. What do I mean by that? I mean, take one of these intervals, like here this is from x being around 0.9 to x being around 1, and then just plug in 0.9 and 1 into the definition, which we're defining here, u is x squared. So the 1, as you see, goes straight down and gets mapped to also 1 in the u plot, and the 0.9 gets mapped over to 0.9 squared, which is about 0.81, or around 0.8, in the u plot. And you can imagine doing this with all of these points and see how the old intervals get either stretched or compressed as we go from the x to the u. So that's shown with this density thing here, right? So this density thing at the top is just a visual thing to show you darker colors are places where these intervals are getting squished together. You see this interval's getting squished. And lighter colors are places where these old intervals are getting stretched out, right, into larger ones. So the punchline of all of this is that this density, this thing where dark colors are squishing and these lighter colors are stretching, this is exactly measuring that function u prime, or I guess, how would we say this? du is 2x dx. This number 2x is telling us the conversion ratio, right? It's telling us how do I stretch or compress an interval in the old thing to an interval in the new thing, right? So that's telling us that, for instance, this the size of an interval around, 1.2 to 1.3, which had a length 0.1 here, is getting stretched to an interval that's around 0.2 in length on this plot. So if you account for that stretching or compressing, you can make the area in the top agree with the area in the bottom. You just simply take areas in the new plot and then rescale them by this stretching or compressing factor to agree with the areas in the old plot. And that's exactly what in U sub, replacing this dx by du equals 2x dx, this thing is doing that stretching or compressing so that you get the right answer. It's a bit of a sketchy hand-waving argument, but do you see the point I'm trying to make?
Yes.
Okay. Thoughts on this?
I don't have any thoughts. This is clear enough.
Okay. Good. All right. So this is just the, I guess, teaser. So this, I think, motivates us to ask, okay, so it sounds like U sub is this thing which always gives us the right answer when we do this. It has a geometrical interpretation, but we're saying it's a meaningless placeholder. So you could ask, all right, it's meaningless for us, but could you develop a new theory? Could you change something about the calculus we're doing so that du and dx do have meaning, so they are well-defined objects, and that these nice, observations we're making here are accounted for in their definitions? So the answer is yes. There are many ways to make these objects du and dx rigorous and meaningful, and they appear in different areas of mathematics, actually. So I'd just like to go through a rapid preview or scripture, I guess, telling you the way that they are rigorized in various subjects. So no need to understand all of this. This is just like a taste of how this is done. So one way you could make du and dx rigorous is by doing what's called non-standard calculus. This is a different way of formulating calculus. So this formulation uses a new number system. Instead of using the real numbers, you use a number system called the hyperreals. What are the hyperreals? Well, the hyperreals extend the usual number line. So what I'm circling in pink, this is the usual number line here. So this thing is what we would call R. This is, 0, 1, 2, 3, 4, blah, blah, blah. Now in the hyperreal number system, you append to the usual number line this pink plot below. So around each number, around 0, you have an extra number line of infinitesimal numbers. These infinitesimals, we use the letter epsilon, to make you think of epsilon delta proofs, basically. Epsilon is a small number. So for instance, an example of a hyperreal number is 0 plus epsilon, or 0 plus 2 epsilon. It's just like in complex numbers when you write a plus bi, right? Some number plus b times I. In the hyperreals, you can have a general number a plus b epsilon. But the rule is that when you multiply two of these hyperreals by one another, so a plus b epsilon times c plus d epsilon, which, just expanding out, you would expect this to be ac, plus you get an ad epsilon, plus a bc epsilon, and then you would think you'd also get this bd epsilon squared. So the rule of hyperreals is that epsilon squared equals 0. That's why we call this infinitesimal. This number is somehow so small that if you square it, it goes to 0. So in this number system, the dx that we've been writing down, this thing in the integral, this dx is one of these infinitesimal numbers, right? Dx is one of these numbers which squares to 0. It's an infinitesimal quantity.
Could you give me a second? It's being very loud in my house right now.
Yeah, sure. I'll be here.
Apologies.
No problem. Good. Anyway, so I won't say much more about non-standard calculus at all. This is just to let you know that this number system exists, but if you wanted to ask, okay, what is dx really? One answer to that question is dx is an infinitesimal number in the hyperreals. That's one answer to the question. Okay. Another answer to the question is you could define a generalized integral. So interestingly, the first proof-based calc course that I took at MIT, which was 18100B, in that class we never even defined the Riemann integral, which is the integral we've done in this group. We immediately went to something else called the Riemann Stieltjes integral. It's a generalization. So I'll just tell you what it is. What is Riemann Stieltjes? The Riemann Stieltjes integral is written integral from a to b of f of x dg of x. So there's two functions involved in this definition. There's an integrand, f, the function you're integrating, and there is an integrator, g. So you think of this integral as integrating f with respect to g. You integrate one function with respect to another. What does that mean? Well, we defined our integral using these upper and lower sums. Remember these sums of, some function value times the difference between the endpoints. So for instance, we defined our lower sum as the sum of the infimum, which we wrote as m sub I, on each interval times t sub I minus 1, or ti plus 1 minus t sub I, right? So we defined our sums this way, I equals 0 to, I guess, n minus 1. So you could say we're going to generalize the lower sum, and of course you remember the upper sum is similar with a capital M. What if you change those definitions so that instead of taking this t sub I plus 1 minus t sub I, the length of the interval, you apply the function g first to those 2 points in your partition. So you take g of ti plus 1 minus g of ti, right? So this gives you a different lower sum and a different upper sum, and you could repeat all of the proofs that we did before to show that this thing defines a perfectly good integral, f dg of x. So if we had started by defining this integral, where you can apply any function to the points in your partition before taking the difference, then we would have said, aha, now we have an interpretation for the symbol dx. The interpretation is that we are integrating f with respect to the integrator g of x, which happens to be equal to x. Right? In that case, dx is simply telling us what g is. G of x is x, which is the simplest case, because then this part just reduces to what we knew before. Okay, so that's a second answer to what does dx really mean. It tells you what the integrator is. Good. A third answer. This is something you'll learn about if you study differential geometry, and this is something I work with every day as a physicist. So when you do differential geometry, you define objects called forms. So what is a form? Or a k-form tells you the sort of rank or degree of the form. So a k-form is something that you integrate. A k-form is what you integrate over a k-dimensional space, over k space. So for instance, a one-form is something you integrate over one-dimensional space like a line. So right, those are like the functions that we've integrated before, because that line is one-dimensional. So a one-form is an object like dx that tells you how to integrate something across a one-dimensional space like a line or a curve. When you study differential geometry, you find a way to generalize this to higher dimensional forms, k-forms, like here is a 2-form. So this is, I'll explain this in a minute, but here's a 1-form, a 2-form, and a 3-form, which you can get by acting with this well-defined object called the exterior derivative d on some function, and then using this wedge product. Wedge product is how you take a form and build higher forms. So the wedge of two 1-forms is a 2-form. So for instance, dx is a 1-form, something you can integrate over a line. Here's an example, dx wedge dy is a 2-form. dx wedge dy wedge dz is a 3-form. And here's the interpretation, the picture for all of these. What are these weird planes that I'm showing? You can interpret forms as sort of a gauge or sort of a kind of like railroad tracks that tell you how much do you weight a particular part of a curve or surface when you're integrating it. So the interpretation is that if I want to integrate something over a line or some curve like this, maybe I'm integrate over this, then the 1-form tells you how much to weight different parts of that line when you integrate. And the way to tell is you ask how many of these planes do you pierce. Right? So if these planes were very close together, then as I integrate, I would pierce a lot of the planes, so that would say count that up more when you're integrating it. But if the planes were far apart, this line would pierce fewer of them, so it would weight the function you're integrating less heavily in that region. Similarly, this 2-form, this is a bunch of intersecting planes. So if I want to integrate some function over some region like a circle, what I would basically do is go to each place on the circle, see how many of these squares I pierce, and take that number and multiply that by the value of the function near that area. So where the squares are close together, I weight the function more. Where they're far apart, I weight it less. And similarly for the 3-form, if I want to integrate a function over a volume, like a sphere that is filled in, like a ball, I just go and, in the same way, see how many of these boxes now I pierce, and that tells me how much to weight the function. So these forms are just different ways of telling you how to weight a function more or less in different parts of space, and you can see pretty visually that you can get higher forms just by wedging together, or taking a 1-form and intersecting it with another 1-form gives you a 2-form. Intersecting that with another bunch of planes here stacked vertically gives me a 3 form. Okay, good. I mean, no need to understand the details because I can't teach you differential geometry in one slide, but the point is this is another way of defining the object dx meaningfully. Okay, one last one, and then we'll do serious stuff, measure theory. So I think you were there when Adam and I were talking about measure theory at my house before JT Talks. He said in his stochastic processes class as an engineer, the professor said, to do all of this properly, we need to do measure theory and the Lebesgue integral, but we'll brush that under the rug. So if you're a mathematician, you learn the Lebesgue integral. It's the most general integral that's in common use. You write it like this, integral of f d mu, where now mu is an object called a measure. What is a measure? Well, I'll try to tell you roughly how the Lebesgue integral is different from the Riemann integral. So suppose we're trying to integrate this function in blue, like this is f or something. We want to integrate this guy. What we were doing before to integrate this guy is partitioning the x-axis into pieces, and then in each partition, you look at the value of the function, pick a point there, and multiply that height times the width of that part of your partition. That's the old way. The new way, by Lebesgue, is a very simple change. Instead of partitioning the x-axis, you partition the y-axis, right? So look, here I'm partitioning up the different heights of the function. So here's one part of the partition. This dt here is the part of the function where the height, the y value, is between this upper value, which is around 3, and this lower value is around 2.5. And when you partition up the range, the vertical part, all you do is for each part of this partition, you look at the pre-image. So you go back to find where in the x-axis do I hit that range of output values, and then you add up the measure of each of these intervals. So you take a measure, which is a function that tells you how big is that interval. So the simplest measure that you would use is just the length of the interval, right? So that's the standard measure. So you could just use a measure which says take the length of this interval, multiply it by this range of output values, and add those up. So you might say, okay, that sounds stupid. All you've done is gone backwards. How could this possibly be different, right? You must get the same answer if now you're just looking at partitions of the range and then adding up the lengths of intervals. That's the same as chopping up the intervals on the x-axis and going the other way. And yes, it is the same in this example. So Riemann and Lebesgue agree, the Riemann integral that we did, they give the same answer if Riemann is defined. So if the Riemann integral exists, then they agree. The reason Lebesgue is more powerful is that you can chop up the y-axis in more instances than you can chop up the x-axis. The simplest example is this function called the indicator on the rationals, which we've seen many times. It's 1 if x is a rational number, and 0 if x is irrational, right? You remember this, our favorite function? He hops around all of the time where he's 1 up here on the rationals and he's 0 down here on the irrationals. And you proved a while back, I think, that this guy is not integrable. Right? You can never get the upper and lower sums to agree because on any partition, the upper sums will always be 1 and the lower sums will always be 0. But if you do this Lebesgue thing, you can actually integrate this guy. Because if you chop up the range, the y values, well, the only part of the chopping you have to consider is this part, the 1, because the rest is 0, so we can just drop that, it won't contribute. Then you just go backwards and ask what is the measure of the place where this function is 1. In other words, what is the measure of the rationals? And it's a fundamental result, which I can't prove for you now, but you would prove at a class on measure theory, that the measure of the rationals in the reals is 0. So therefore, the Lebesgue integral of this function, indicator on the rationals, d mu, where mu is the standard measure on the real numbers, is 0. So this is a case where Lebesgue gives you an answer, but Riemann doesn't. Okay, so now you might say, all right, fine. So now I know what d mu is. D mu is a measure. That's a very important thing. Is there an interpretation for U substitution? And the answer is yes. There's a beautiful theorem called the Radon-Nikodym theorem in measure theory, which tells you how to change measure. Right? So if you want to integrate a function g with respect to one measure mu and with respect to another measure lambda, you can take a particular derivative called the Radon-Nikodym derivative of one measure with respect to another, and it tells you how to convert between the two of them. And as you can see, this equation looks just like U substitution, except now these are measures. Right? It looks just like, du dx canceling or something. Okay. So that was a really fast summary of basically a lot of advanced undergraduate and graduate math, which maybe didn't make a lot of sense, but I included just because I wanted to geek out about it. So do you have any thoughts or reactions to any of those 4 interpretations of dx?
You're correct. It made 0 sense.
Good.
I found myself interested in the hyperreals, though.
You like the hyperreals? Okay. Good. You should also go on Wikipedia and read about the surreal numbers. So the surreal numbers extend the hyperreals. Very interesting.
What a definition.
Quite funny, actually.
I mean, word. That's what I was looking for.
Yeah, good choice of word for it. Okay. Even though it didn't make any sense, did you feel happy listening to that, or did you feel bored?
I think bored.
Okay. Good to know. Useful feedback. All right, let's go on to something more relevant then. Let's just summarize all the integration techniques that we've done. Good. So I'm just going to list them. These are, I think, kind of the integration techniques every practicing scientist or mathematician should know. So the first 4 in black text, I expect you to be able to basically recognize and use them cold, like just knowing all of these, U sub, parts, partial fractions, and trig sub, which you used all of, I think, in your tutorial. The blue ones we discussed, but I don't expect you to know off the cuff. Just know they exist, right? Like this Weierstrass, the reduction formula, the Feynman trick, differentiation under the integral, inverse functions, and contour integration, which is really complex analysis. So I just want to go through each of these really quick as one last review. So here's U sub again. Recall we proved this using the chain rule, right? So this is just the chain rule backwards, that integral of some on the right side, f of g of x, g prime of x dx, you can change variables and integrate u, right, from g of a to g of b. A familiar result. Here's an example. If you want to integrate xe to the minus x squared, the way to do it is let u equal 2x, du is 2x dx, and then you simply take this x dx and replace it by a half of u. This is a known integral. Pull down the minus 1 by the chain rule, and then put the u back in at the end. So it's minus a half e to the x squared. Good. Easy peasy. Parts. Remember, so we proved this again using the product rule and integrating both sides. Integral of fg prime is fg minus integral of f prime g, or ab prime, however you want to remember it. Example, to integrate x cosine x, we want to move the derivative from cosine onto x. So you let f be x, f is the one you differentiate. You let g prime be cosine, that's the one you integrate. And then using the formula, fg is x times the integral of cosine, which is sine. So x sine x minus this f prime g, f prime is 1, so integral of sine. Integral of sine is minus cosine, which kills the other minus sign, so our answer is x sine x plus cos x. Good. Should be second nature by now. Good. Partial fractions, it's not really calculus, this is just algebra, a way of taking a polynomial and splitting it into a sum of terms. So for instance, for this x squared plus 2x minus 3, the first step is to factor it. So you can see that x plus 3, x minus 1, gives us the original quadratic, x squared plus 2x minus 3. So you split this into a sum of constant coefficients over the two roots, and then you solve for a and b in the usual way. Multiply both top and bottom here by x minus 1, and here by x plus 3. Then you get two equations by matching coefficients, so you get a plus b equals 0, and 3b minus a equals 1, which has solution a equals minus a quarter and b equals a quarter. And then you just integrate these directly to logs, or this time I've remembered the absolute value. Good. Last one I expect you to have basically memorized, trig substitution. The 3 tricks you just remember, if you ever see expressions of the form a squared minus x squared, a squared plus x squared, or x squared minus a squared, you make the trig sub that looks like the corresponding Pythagorean identity. And you can always derive these other Pythagorean identities by starting with the sine and cosine one and dividing. Right, so for instance, if, as it is down here, an expression involving x squared minus a squared, which is 0.3, like this integral, you make the substitution x is a times the secant of theta. Why secant of theta? Because we have x squared minus a squared, and if x is a secant theta, then this expression turns into a squared times the quantity secant squared theta minus 1, which is tangent squared of theta. Right, so example, make that substitution in this integral. When you put in x as a... Oh, did I do this backwards? Yeah, I switched them for some reason. Whoops. The integral I'm actually doing is x squared minus a squared. So I really want secant, as I said. Yeah, so ignore everything I said here. Damn it, yeah. I messed up these two. I used the wrong one that I said here because now this is, I've gone backwards. Okay, so the typo is actually here. This should be written as integral dx over root a squared minus x squared. Good, all right, so if that's the integral, then indeed you should use the first one. So, okay, fine. Without the typo, you let x be a sine theta. This becomes a squared times the quantity 1 minus sine squared, which is cosine squared under the square root, or cosine upstairs. Meanwhile, we get a cosine downstairs. Meanwhile, we get a cosine upstairs from the dx. The cosines cancel. The a's cancel. This is the integral of 1 d theta, which is theta. And then solving for theta in our definition, it's simply arcsine of x over a. Okay, hopefully this is all painfully obvious, but thoughts or reactions to the first ones I expect you to know?
I do not have any reactions thus far.
Okay, good. All right, so let's do one more run through of the ones that I don't expect you to have memorized, but I want you to recognize, right? So what is the cue to make you recognize Weierstrass? Whenever you have a rational function of trig functions, so it means a ratio of maybe a sum of trig things upstairs and a sum of trig things downstairs possibly, it's usually best to use this half-angle substitution, where you let t be tangent of x over 2. So the example is, for instance, if you want to integrate cosecant, which is 1 over sine, this is kind of a simple rational function of trig functions. You make the substitution, t is tan x over 2. After a short calculation, you can show that that means sine of x, using this half-angle thing to simplify it, which we went through when I did the 2014 integration B. You can show that that means sine x is 2t over 1 plus t squared. This dx comes from differentiating both sides of this. You get a dt, and then the derivative of tangent, or sorry, solve this for x by taking an arctangent, then hit both sides with a d, and the derivative of arctangent is 1 over 1 plus t squared. You get a 2 from this 2. So that gives you this. You plug those both into the integral. 1 over sine means take this thing and invert it. Invert. So we have a 1 plus t squared upstairs, a 2t downstairs. Here's the dx, the 2 over 1 plus t squared. And the beauty of the Weierstrass substitution is these guys cancel beautifully, and we're left with just the t downstairs. So integral of 1 over t is log t, and you put the t back in. It's a log tangent of x over 2. So just remember this trick, the half-angle thing, if you ever see rational functions of trig functions. Good. The other, so the nice Feynman trick, so remember we use this to prove, and it's something we will use again and again, this integral that minus infinity to infinity e to the minus x squared dx is root pi. We prove this using this technique. So what is the technique? If you see some hard integral, what you can do is define a new integral, we typically call it I, which depends on a new parameter which you make up, usually b. Then you can differentiate I with respect to that parameter b, and if you've done it cleverly, you can evaluate that derivative and then integrate it to get some answer. So here's a nice example. If you want to integrate from 0 to 1, the ratio x squared minus 1 over log x. So a nice way to do this is make up the new parameter b and use it to replace the 2. Right, so I, now depending on a parameter b, is the integral from 0 to 1 of x to the power b minus 1 over log x. So now I'll ask you as a challenge to walk through the steps for how to use this to actually evaluate the original integral. So the scaffold is first, I'll ask you to walk me through this. How do I show that the derivative of I of b is log b plus 1 plus some constant? So what should I do? Did you mute yourself?
Wow, that was interesting. I unmuted myself. You said, did you mute yourself? And then I realized I muted myself, actually.
Good. Now that you're unmuted, what do I do?
Let's see. I believe that we can start by taking the derivative of each side.
With respect to what?
With respect to b.
Good. I'm going to use this symbol, which you haven't really defined, but I like it for using derivatives when there's two variables. So I'm going to use this curly b. So I call this partial. So we take partial b on both sides. So what do I do on the right side?
I believe that on the right side we are going to get, well, let me think. Trying to remember how to handle some constant to the power of our variable.
Yeah.
I'm tempted to believe that we should use e to the log, but I don't know if that is totally correct.
You can do that. So, okay, let me write the intermediate step. So the first step, which we proved in session, is that we're actually allowed to move that integral past the derivative, right? So that's one nice thing. So
Yes.
This should be, now remember, this is a derivative with respect to b, so x is a constant. It doesn't see this log x. And then, as you said, we really need to figure out what is ddb of x to the b. Okay, so let's do that up here in a sidebar. So your suggestion was e to the log? Sure, so let's do that. ddb, how should I do this? E to the, what, b log x or something? Is that what you want to do?
Yeah.
Okay.
I don't know if that helps us, but...
Yeah, sure. So what's this derivative? You know how to do that.
The derivative of that is going to be log x e to the b log x.
Good. Log x e to the b log x. And then can you simplify the second part now? Just put it back.
We put the b back in and see that we get log x times x to the b.
Yeah, good. Now you see why this was such a clever choice of parameter, because what happens under the integral now?
Let's see. I see that the log x's are going to cancel, at least for the first term.
Is there a second term?
No, there is not, because the derivative of -1 is 0.
Good. So what do I get in that first term after the cancellation?
Simply x to the b.
Good. X to the b. This is all dx. Now, how do I evaluate this integral?
I believe that we let b equal... No. Are we letting b equal anything?
Nope, this is a function of b, so b has to be left arbitrary.
Okay. Thinking. Are we going to place this, well, e to the power of stuff again?
You could if you want.
Just by equivalency, or is there a more direct route?
Well, what's the integral of, I mean, x squared or any, now b is some number, right? So how do you, this is power rule, right? How do you integrate x raised to some power?
Are you serious?
I think so, unless I'm confused.
I think we've been, I swear we've been treating x as constant.
You have to be careful. When you take a derivative with respect to b, x is a constant and b is a variable. Now we're integrating with
Now
respect to
it's...
x. We've switched. You always switch in these problems, right?
Okay. Yeah, it's just going to be ... I think. X to the b plus 1 over b plus 1.
Yeah, x to the b plus
Well,
1.
big boys
Yeah.
surrounding it. Context necessary.
From 0 to 1, right?
Yep.
And then what does this evaluate to?
That is going to evaluate 2 when it's equal to 1. X squared over 2 minus... X over...
Wait, hold on.
Wait.
You're plugging in 1 for b. 1, this is x. X equals 1 to x equals 2. Integrate with respect to x, right?
Yeah, so when it's 1, it's 1 over b plus 1.
1 over b plus 1. And then the other one is 0.
Minus... Yeah, minus 0.
Yeah, minus 0. And now I made a typo because that shouldn't be a prime, I'm realizing. Good. Okay, so what we just found was the derivative. Let's just remind us. So we found that the derivative of I with respect to b is 1 over b plus 1. So what does that mean, the function itself, not the derivative? What is I of b then?
It is going to be log of b plus 1 plus c.
Yeah, so just now be careful, because to solve this, what we really just did was integrate both sides with respect to b, right? So now b is a variable again when you're integrating. Good. All right, so that's the first part. So we found what I of b is. Okay, thoughts or questions on the first part, or is this all clear?
No, it is all clear.
Okay. Yeah, just be careful about what's a constant and what's a variable in each step. Good. Okay, so we've got that. I'll erase the work because now we know the answer to part 1. Now, how do I evaluate what c is? Can you think of a value? Can you pick a particular choice of b such that we know what I of b is, and then use that to find what c is?
If we let b equal 0, we have the line 0.
Yeah, because you integrate from 0 to 0, which is 0. And then what's the right side of this when b equals 0?
That is going to be 0 plus c.
Yeah, so what must c be?
C must be 0.
Good. Okay, so we've done part 2. Good. C is 0. All right, third.
Argue.
What'd you say?
Argue.
Oh, argue. Good. Thank you. Okay, so now we have this thing. So we know I of b, which is this thing, this integral when x is raised to the power b, this thing is equal to log of b plus 1. So how do we use that to solve the original question we wanted to answer, which is this thing?
I believe we let b equal 2.
Perfect, yeah. So indeed, what we wanted to find in the first place was I of 2, which is log of 2 plus 1, which is log 3. That's it.
Whoa.
So it's not hard, right? Let me just emphasize that this technique is so powerful, because if you stared at this integral at the beginning, there's no fucking clue in my mind how to do this, right? Clearly U sub doesn't work. I don't know what to do with parts. This looks very complicated. The only trick, the only thing which was hard in this step was recognizing that you should introduce a parameter b, let the exponent be changing, and then the rest is just very easy, just direct manipulation. This is why Feynman was a god. All right, cool. Thoughts on this?
No thoughts.
All right. Good. All right, so let's review the last couple. So we only discussed this briefly, but I just want to mention it again. We proved this in 3 different ways, right? How do you integrate the inverse of some function? So what we showed is that if you know the integral of the original function f, so integral of lowercase f is capital F, and you want to know how to integrate the inverse function, so integrate f inverse, we proved that here's the answer. You just take y times f inverse and then subtract the integral of the original function composed with the inverse function itself. All right, this should remind you of the derivative rule for inverse functions, right? This was 1 over f prime at f inverse of x. This is really just that backwards. So why is this powerful? Okay, well fine, suppose I want to integrate arctan. Here's an easy way to do that without a lot of work, like integration by parts. You just say, all right, I want to integrate arctan. I know that's the inverse of lowercase f, which is tangent, right? Because arctan is the inverse of tangent. I know what the integral of tangent is, because that's just log of cosine, so I call that capital F. And then I just use this formula. So replacing y with x, the first term is x times the original function itself, which is arctan. And then the second term is, well, I take the integral of the original function, so that's log of cosine. And then I plug in the function I'm trying to integrate, which is arctan. So it's log of cos of arctan. And then if you really want, you can just simplify this. We know how to simplify what cosine of arctan is. What is cosine of arctan of x? Well, hopefully this is second nature by now. So you say, all right, I want to find the cosine of an angle whose tangent is x. So suppose the tangent of theta is x. Tangent is opposite over adjacent. So if opposite over adjacent is x, I might as well let this be x and let this be 1. By Pythagoras, this is 1 plus x squared. Now the cosine of my angle is adjacent over hypotenuse, so this thing must be 1 over root 1 plus x squared. And then you say, aha, but that's all inside of a log. And by log of a power, this is that thing raised to the minus 1/2 power, so I just pull out the minus 1/2, and then it's log 1 plus x squared. Done. No integration by parts, no nonsense, just applying a formula. Good, okay. Last one, and then on to more stuff, so last thing of review. And I don't really expect you to know this, but it's such a powerful technique in higher mathematics that I just want to remind you of it one more time. Oh, sorry, first reduction formulas. Yeah, then the residue stuff.
What does that say? I don't remember you really making a big deal out of reduction formulas.
No.
Other than being a shortcut.
Yeah, this is just a shortcut. This is not a big deal at all. But I will remind you that you can prove these nice formulas that relate families of integrals. So here's the tangent one, which Steve wanted you to use on the integration bee. I'll just prove the reduction formula for tangent. So define this integral I sub n.
Just Steve.
Yeah, Steve Wolfram, man. So if I sub n is the integral of tangent raised to the power n, we can derive a reduction formula. All you do is use this Pythagorean identity, tan squared is secant squared minus 1, right? So I take this tangent raised to the power n, I write that as tangent to the n of x is, I peel off 2 factors of tangent. So it's tangent squared times tangent to the n minus 2 of x, right? So I just split it to pull out a tangent squared, and then I replace the tangent squared with the secant squared minus 1. So when I peel that off and then distribute the tangent squared onto each of these, one of them is easy. The second term is the integral of tangent to the power n minus 2, but that's the definition of the integral I sub n minus 2, right? Because that's just the integral of tangent raised to some power. Here the power is n minus 2. For the first one, all I have to do is evaluate integral of secant squared tangent to the power n minus 2, where I'm not writing the x's, but let u is tangent x, du, we know the derivative of tangent is secant squared x dx, so this thing becomes integral of u to the power n minus 2 du, which is simply the power rule, u to the n minus 1 over n minus 1, and then plug back in, and u is tangent of x. So that's how you derive the reduction formula for tangent. And on your integration bee, you actually went through this with n equals 4, right? You integrated tangent to the 4th and did exactly this. So yeah, this is not a powerful technique. It's just nice to know they exist, and they're compiled in tables. Good, okay. And then one more, I want to remind you of this, because if you ever study complex number calculus, the most powerful theorem, the analog of the fundamental theorem of calculus that we have, is called the residue theorem. So if you ever want to integrate some complex function around a curve gamma, all you have to do is look for places where the function blows up inside that curve, and then compute something called the residue at each of those poles, where the residue is the number that appears over that linear blowup, this factor z minus a, if this thing blows up at a. So there's an example of that we had in session, just that if I want to integrate this function, which looks like this, it's a bunch of rational expressions in z, and I want to integrate it over this red curve gamma, All I have to do is find the places where it blows up inside gamma. So it blows up here at z equals I because of this blowup, and it blows up here at z equals 1 because of this blowup. And then I just extract the number over the linear part of the blowup. So this guy contributes no residue because he has a quadratic blowup instead of a linear one. And this guy contributes a residue of 2. And then it's very easy, I'm done. The integral over gamma of f of z, it's 2 pi I times the sum of the residues. And the sum of the residues is simply 2. 2 times 2 pi I is 4 pi I. Very powerful. Good. That is the end of the review part. So, questions or last comments as we end integration techniques on any of this stuff?
Is my mic working? Yes.
Yes.
I don't have any final thoughts.
Okay. All right, one thing that I need to do to wrap up, this is something I claimed and you had to use on the integration bee, but I never proved. So I'll just sketch the proof and tell you it, so then after that we can just move on. So here's a theorem. This is the general case of partial fractions. The hardest part of this theorem is just understanding all of the notation. So the theorem is let p and q be two polynomials, which I'll just write like this. P is going to be our numerator, and we write it in the usual way, x to the power n, a to the a sub n minus 1, x to the n minus 1, down to a0. Q is another polynomial of degree m, but we're going to assume that it can be written in this way as a product of factors. So it has some linear factors. Q has a bunch of linear factors, and it has a bunch of irreducible quadratic factors. I'll say more about that on the next slide. So it has some quadratic factors. So the theorem is that if P and Q have this form, and you would like to understand the ratio P over Q, this rational function, the theorem is that there always exists a polynomial T of x, which you can think of as getting from doing polynomial long division. This is the first piece you get before remainder. And then the theorem says there exists some numbers a, b, and c, such that that ratio can be written as a sum of terms that all look like some number over each of those linear factors, right? X minus alpha sub I, raised to some powers. So you can have each of these linear factors raised to different powers up to the power with which it appears in Q. And similarly a sum of the quadratic pieces. These are sums of some linear term, bx plus c, divided by the irreducible quadratic pieces. Okay, so this is just the partial fractions we know and love, but written in a much more general way. So for instance, if you had something like p is, I don't know, 3x plus 5, and q is, I don't know, x minus 1 squared, x plus 1, the theorem is telling us that the ratio 3x plus 5 over x minus 1 squared times x plus 1 can always be written as a bunch of numbers where, and be careful about the ones I'm including here, it's some number a over x minus 1 plus a number b over x minus 1 squared plus c over x plus 1. You say, why did you include both of these, x minus 1 and x minus 1 squared? It's because the theorem tells us that for each of the linear factors, you have to sum up the exponent j in that linear factor from 1 up to the power with which it appears in the original expression. So here it appears with a 2 in the original expression, so we have to sum up this thing raised to the first power in one piece, and it raised to the second power in another piece. That's how it works out in general. But before going on to the comments about this, questions or observations about this ugly as fuck formula?
Now I believe I understand what is going on.
Okay, good. So I'll sketch the proof, but first a remark. Yeah, proof sketch on the next one. So I'm surprised you didn't object immediately. Why didn't you object, I wonder, and say, why do we...
I imagine... Okay. Just my thoughts toward this was basically there doesn't necessarily need polynomial functions don't necessarily need to break down into binomial factors, but
Yeah, can you give an example of one that doesn't break into binomials, for instance?
I think x plus 2 squared plus 2.
X.
I mean, no, x plus 2 plus x squared plus 2 x plus 2. There we go.
X squared.
I do not believe that that breaks down. Oh wait, it does.
X plus.
Yeah, use quadratic formula. Or just guess. Never mind.
Well, let's use the formula and see what we get. So negative b plus or minus the square root of b squared is 4, minus 4 times a is 1, times c is 2, over. So you actually picked a good one. This is an example. This does work, and it works for the following reason. Because
Does it account for imaginary roots?
That's exactly the point. No, this theorem is assuming all of these numbers are real, right? So this is exactly the point I'm getting at. Under the square root here, we have 4 minus 8 is minus 4. So this is 2 plus or minus 2i over 2. So the two roots of the quadratic you just told me are minus 1 plus or minus I. So if you wanted to break this quadratic into two linear pieces, what you would have to do is write it like this. You would have to write it as x minus the first one, which is minus 1 plus I, times x minus 1 minus I, which I'm not distributing out. So that's exactly the sort of thing this theorem is accounting for. The reason we include these quadratic factors in the general case is because we are not allowing these product of binomial alphas to be complex. If we allowed the alphas to be complex, you would not need to write these quadratics, and you could say every polynomial can be partial fractioned into linear pieces. But because we don't allow complex roots in ordinary calculus, this isn't complex number calculus, this is ordinary calculus. Since we don't allow those, you have to say, aha, this quadratic you wrote down cannot be reduced. It is what we call an irreducible polynomial, irreducible over the reals. But of course it is reducible over the complexes, because everything is reducible under the complexes, or over the complexes. That's the fundamental theorem of algebra, that every polynomial...
Okay. Now I must ask, can every polynomial break down into some multiplication of binomials and trinomials?
Yeah, every polynomial over... split into binomials and trinomials over the reals, you mean? Is that what you're asking?
Yes.
Yes, exactly. Yeah, that's part of this theorem, actually.
Is there a proof of that?
Yeah, it's... How do we prove that? Yeah, I could prove that. Okay, so we can't. I don't see how to prove it with the techniques that we. No, I do know how to do that. Okay, I can prove it right now. I just thought of a cute proof that doesn't use abstract algebra. Okay, am I allowed to use as an intermediate step the fundamental theorem that it splits into linear factors over the complexes first? Can I do that?
Sure.
Okay, here I'll prove it for you. This will be fun. Okay. Theorem. So. Theorem.
Oh, I already see.
You see what I'm going to do?
Yeah.
Tell me what I'm going to do.
Are you going to write down all the binomial roots and then multiply all the binomial roots that contain an I?
Yeah, do you see why they're going to pair off nicely?
Yeah.
Why?
Actually, no, I don't see why they're going to pair off nicely. How do you know that there's an even number of imaginary roots?
Yeah, that's the key part of the proof, is knowing that there's an even number and they pair. So let me tell you. I'm going to write this theorem in a sloppy way. So every polynomial p of x splits into linears and quadratics. So as you call them, binomials and trinomials. But okay, so proof. This is the important part. Let p of x equal, so we start with a n x to the n, and then give all these guys names, right? X to the n minus 1, dot, 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 plus a0. And we're going to assume the coefficients are real, right? So all of the a's are real at least. The roots aren't real, but the coefficients are real. Are you happy with that assumption?
Yes.
Okay, so by the fundamental theorem of algebra, this is my intermediate step, p of x equals, so it splits into n roots, right? There's n of them with multiplicity, because this is to the power n. So I'll call the roots alpha. So x minus alpha 1, dot 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 x minus alpha n, there's n of them, where, okay, some alpha I are complex. Okay. Now here's the key part. Take the complex conjugate, the bar, take the complex conjugate of both sides of this equation. Okay, this is the key part. So take the complex conjugate of both sides. So first let's think about the left side. The complex conjugate of p of x, what does that mean? The complex conjugate means basically every time you have a plus bi, what's the definition of the complex conjugate of a plus bi again?
A minus bi?
Yeah, a minus bi. So if there's no i's, if a number is real, what's the complex conjugate of a real number?
A.
A, good. And we assumed p of x, all of those coefficients a are real, right? So what's the complex conjugate of p of x?
P of x.
Yeah, so p of x, what's the complex
Log
conjugate?
wow.
Yeah, so the complex conjugate of the right side, x is real, so it's x minus alpha 1 bar dot 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 x minus alpha n bar. Okay, now here's what I do. The left side of both of these equations are equal. They're both p of x, which means the right side of both of these equations are equal. Right, so all of these products x minus alpha I are the same as the x minus alpha I bar. What does that buy us? That means that since all of these products are equal, I'm going to erase this and start over. That means, oh, made that too thickica.
Thick. So it's a 7 Ks.
7 Qs, thank you very much. How do I make it less thick? Fucking hell. All right. So that means, anyway, what did we just prove? I'm going to use it thick until I figure out how to fix it. So x minus alpha 1 dot 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 x minus alpha n is equal to x minus alpha 1 bar dot 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 x minus alpha n bar. So if these two things are equal, then that means every alpha I which appears in the top must appear in the bottom. So in other words, the set of all the alpha I is equal to the set of all alpha I bar. So what does that mean? If I have a set of numbers and I complex conjugate every number in the set and I get the same set back, there's two possibilities. So two options for each alpha in the set. Either a given alpha is real, right? So alpha I is real, because if it's real, clearly complex conjugating it will leave it in the set. The other option is both alpha I and alpha I bar are in the set. Why is that true? Suppose by way of contradiction that alpha I were in the set, but alpha I bar were not in the set. Then when I take the complex conjugate of every element of this set, that set has alpha I bar, but I assumed by way of contradiction that alpha I bar was not in the set, so these two things cannot be equal. Do you agree?
I'm just in deep thought. I'm thinking.
Yeah, so what I'm saying is that if you have...
I know exactly what you're saying. I'm just thinking about what that means.
Yeah, the meaning of this statement is that every polynomial...
I mean, not what that means. Thinking about the AI and AI conjugate.
This thing. Yeah, all I'm saying is that roots of polynomials always come in complex conjugate pairs. That's the thing I just proved, right? Because otherwise those two would not be equal. Okay, so let's finish the proof then. What does that imply? Thus, we can pair off every alpha I and alpha I bar as follows, right? So we already said p of x is a combination of, let's see, x minus, let's put all of the complex ones at the end, right? So assume that you have, all of the real ones come first up to alpha k, and then suppose after alpha k, without loss of generality, otherwise just change the order, so all the complex ones are at the end. So we've proven that for every complex one, he appears with his conjugate, so there's an even number of them, and they come in pairs. So we have x minus alpha, say k plus 1, and we pair that guy with x minus alpha bar, k plus 1. And you keep doing that until you get to the last complex one, x minus alpha n, x minus alpha bar n. And then the claim is that for all of these pairs of complex ones, just FOIL them out. Because if I FOIL this out, I get x squared minus alpha n plus alpha n bar x plus alpha n bar. And this is a quadratic with real coefficients. Why are they real? Any number plus its conjugate is real, because obviously a plus bi plus the conjugate a minus bi, the i's cancel, it's 2a. So if you add a number to its conjugate, it's real. So this is real. And a number times its complex conjugate is real for the same reason, because the cross terms cancel. So that concludes the proof, because now it's a product of linears and quadratics with real coefficients, as we claimed. Good? You agree?
Yes. I'm just thinking more about how... Is it true that I think. Let's say you have a third-degree polynomial with 2 real and 1 imaginary root.
Can't.
Okay.
I just told you every
Yeah,
complex root comes with its conjugate.
I'm just trying to think about writing something down. And
if you wrote it down, it wouldn't have real coefficients. That was the assumption we made at the beginning. So you just say,
yeah.
Suppose we have 2 real and 1 imaginary.
Yeah.
Let me just cook one up.
I see.
X plus 1, x minus 1, x minus I, right? If you FOIL this out, it won't have real coefficients. That's the claim. I mean, we could just,
I see.
I mean, let me just do it for closure. Expand x plus 1, x minus 1, x minus I, right? It can't have real coefficients, and indeed, the coefficient of x squared is minus ix squared.
Yes, I see now.
Good. I mean, I can't tell if you're bored or enjoying this, but I'm having a lot of fun with this question. Are you satisfied with that claim? Did you mute yourself again?
No, I'm just thinking.
Is it a good thinking? Let me know when you've...
I'm trying to think if there's any cases of the quadratic formula where it's plus some positive root and minus some negative root. Wait, no. That's not how it works. Oh my...
Plus or minus a square root, right?
Yeah. So it's either both are imaginary, both are real.
Yeah. For quadratics, that's true. For higher degree, you can have different ones. Or you can have a double root. If it's plus or minus, if the discriminant is 0, right, then you have a double root. That's the only other possibility. Good. These are very good questions. Do you have more thoughts on this?
I would not have expected this to be like a bombshell.
A bombshell in the sense that you're interested in it, or?
Yeah. It's just
It's a very interesting point. So just to remind us, what did we just prove? We just proved that you can take any polynomial with real coefficients and split it this way. Write it as...
Yeah. We proved it. It makes so much sense and so little sense at the same time.
Yeah. It's a powerful, nice result. I'll comment that you study questions like this more in an abstract algebra class. So for instance, you can ask questions like, so here's the remark. We already said a lot of this, but let me just say it again. You could ask, why do you need quadratics, right? Why do you need to split this polynomial into products of linear and quadratic factors? So here's one example. If you want to split x over x cubed minus x squared plus x minus 1, and you notice that, okay, that looks like this, x minus 1 times x squared plus 1, the best you could do for partial fractions is writing it like this, a half over the linear piece, and then this linear over the quadratic. And then as we just saw, you can't split it further over the reals because the roots of x squared plus 1 are plus and minus I, x plus I, x minus I. If we were allowed to split split partial fractions over the complexes, you could partial fractions that quadratic like this, right? You could write it as I over 2 over x plus I and a minus I over 2 times x minus I. Same reason that we did before. But if we're working over the real numbers, we say this polynomial is irreducible. So this leads to a very deep subject, which is factorization domains in abstract algebra. And if you take a course like 18702, you'll ask very general questions like, what are the rules by which I can tell whether a polynomial is allowed to be reduced over some arbitrary field? A field is a set of numbers like...
Sorry to interrupt, but I suddenly realized that any polynomial's degree can be built out of sums of 3 and 2.
Any polynomial's degree can be built out of sums of 3. What do you mean? You just mean
Like,
any number. Any number can be written as some...
Yeah.
That's just...
I'm just thinking because the quadratic and linear parts.
That has nothing to do with polynomials. That's just the statement that any integer can be written in this form for some case.
I don't even know how it's irrelevant. I'm just thinking.
These are good thoughts, though. Other thoughts
No
on
idea.
polynomials?
No.
Okay, good. So I'll just say one more comment. Yeah, if you want to study this more and ask the question, suppose I generalize polynomials and I just say, you know, I'm going to take polynomials where the coefficients lie in some general field f. Field f could be the real numbers, the complex numbers, it could be the integers, it could be the Gauss integers. Gauss integers are something like, I don't know, C of 2 or something, which is the set of all integers n plus 2 I. Is that right? No, sorry. That's not what I want. Sorry. Gauss integers, I don't know what the symbol for it is actually. Gauss integers is just the set of all numbers n plus mi, where n and m are integers. So that's another field. So you can ask the question, how do I tell whether a polynomial is reducible if I'm only allowed to write its roots if they belong to a certain number system, a certain field? And there's a whole field of study, all these rules, this Eisenstein criterion. Let's see, do this. Not Einstein, Eisenstein criterion. So you could take basically an entire class where you study this question in abstract algebra and study polynomials in complete generality. So it's very deep. I'm glad you seem interested in it, at least in the real number case. Okay.
Spooky.
Very spooky. All right, so I didn't prove it. Let me just prove. So we proved the first part, which is proving that every polynomial can be written as a product of linears and quadratics. What about this thing, that you can write, you know, this huge-ass sum, that it always splits like this? And I'll cheat a little bit and use a result from linear algebra, which you kind of know. So here it is. We're trying to prove that there exist, you know, these aij, bij, and cij, possibly with a polynomial t, such that this equation is true. So it's enough to prove that we can solve to find a choice of a, b, and c. How would you find them? Well, if we multiply, that's a typo, if you multiply both sides of this equation by q of x, then since q of x has each of these things in the denominator as part of its expansion, because q is a product of all of those, then you can see what's going to happen in each term. Q of x is going to cancel the denominator and then have some other stuff left over when you multiply through both sides by q. So now there's no denominators on the right side. Now we have an equation whose left side is simply p of x, which is a polynomial of degree n. And the right side is just a linear function of these coefficients, a, b, and c. So this is a bunch of, you know, a's times the coefficients of q, b's and c's times the coefficients of q's, and this t. So since this is a bunch of linear equations, because we can set the coefficients of each of the powers of x equal on the two sides of this equation, we get n equations basically by setting those n things equal. Now there's a theorem in linear algebra that every set of n linear equations which is non-singular has a unique solution. What do I mean by non-singular? I mean, we can think of this entire equation as some matrix. The matrix is just all this junk that's happening on the right side. So there's a bunch of numbers in here which we don't know. Some giant n by n matrix acting on these coefficients that we want to solve. So there's a bunch of aij and a giant vector, a bunch of bij and a bunch of cij, and they're equal to the known coefficients of p on the left side. So I don't know, p0, p1 up to pn. And the reason there's a unique solution is because this determinant has, this matrix has non-zero determinant, so you could solve this equation by simply multiplying both sides by the inverse matrix. You multiply by m inverse on both sides, get the identity on the left, on the right side you get some numbers, and then you simply say A is equal to the first one, B is equal to the second one, and so forth. So this proof doesn't tell you what those A, B, and C are. It's simply a proof that they exist, which means we can always write this partial fractions decomposition. It's always possible to do it. Okay, it's not a very detailed proof, but it's correct at least, just sketchy. Thoughts on this?
Stand by while I unmute myself. I don't have any thoughts.
Unmute myself.
Unmute. Whoops.
Whoops. Okay.
Vote with 3 O's.
With 10 Q's. All right, a challenge for you since I've been doing a lot of talking. All right, suppose we want to integrate this guy. This uses what we just learned, that if you have 2 linear factors in the bottom, you have to write partial fractions that has one guy with the linear factor to the first and one guy with the linear factor to the second power. So, all right, how do I find A and B and compute this integral?
So we can multiply A times the 1 minus 2x squared.
Squared or to the first?
To the first, apologies.
Yeah.
Because it's already over 1 minus 2x.
Yeah, we're just getting a common denominator, right?
And do we need to multiply B by anything? Or do we need to multiply B by 1 over 1 minus 2x?
We're trying to get all 3 terms to have the same denominator, 1 minus 2x squared.
Oh, so we don't need to do anything to B. Okay.
Good. All right, so now what do I do?
So we're going to write down the equation A minus 2ax plus B equals 3x plus 5.
Minus 2ax plus B equals 3x plus 5. Good. Then what?
Which implies that A plus B equals 5.
Okay.
And negative 2a plus 0b equals 3.
Good. Solve those for me.
A equals negative 2/3.
2/3 or?
Oh, 3/2, sorry. Yeah. And thus, I think 5 plus 3/2 equals ... 13/2.
Yeah.
What? Yeah.
Equals. Sorry, I was just doing the intermediate step for myself.
I was like, oh god, what did I do?
Good. Okay. So this guy breaks up into minus 3/2 over 1 minus 2x. And as you say, a 13/2 over 1 minus 2x quantity squared. And then now all we have to do is integrate both sides. So as I erase, think about and then tell me what the integral of those terms are.
Let us factor out the constants in the numerator.
Okay.
And then we're going to simply find trying to figure out how to handle the... I know that the first term can be written as negative 3/2 times 1 over negative 2 log of 1 minus 2x.
Good. 1 over minus 2. What I always do is say, all right, I know it's some number times log 1 minus 2x, and then I put in the number to cancel this thing, but as you already did that for me, you need the minus 2 to cancel that. Perfect. What about the second guy?
The second guy. Deep thunk. I feel like this should be exceedingly obvious, but I
Well, it's power
need to
rule.
think. Oh, come on. Okay, so we apply the power rule. Once again, 13 halves times 1 over negative 2? Because we're going to get a negative 2. I don't know.
Well, let's put this in. Let's put this times something and then figure out what the number has to be, right? So it has to be this. We know the third part is this to the power minus 1, right? So 1 over this, right?
Yeah.
Good. Now, when I take a derivative of this, what do I get out? Or let me write it a little more suggestively. That's 2x to the minus 1.
Yeah.
Okay, now what?
I feel like this is the chain rule.
Yeah.
So it is going to be, I think, negative 1 minus 2x, well, negative, begin parentheses, 1 minus 2x to the power of 0? No, I mean, oh god, I can't remember if we multiply it by the new or old power.
Okay, so when you differentiate, it's minus 1 times 1 minus 2x to the power minus 2, which gives us this, as it should be, times the derivative of the inside, which is minus 2. So all in all, I multiplied by a minus 1 from the power rule when I pulled this out, and then I multiplied by a minus 2 from the chain rule. So what should I put here to soak up minus 1 times minus 2?
A 1/2.
Yeah, 1/2. Good. So that's actually it, because then our answer, just doing some arithmetic, is 3/4 log 1 minus twice x plus 13/4 times 1 over 1 minus 2x. Good. Let's see if we actually did that correctly. Indeed. So, yeah, 13/4 1 minus 2x to the power minus plus, yeah, it matches.
Did we actually need to, we have, yeah, okay. The order was swapped around, yeah.
Yeah, sorry, for some reason I wrote it this way, but yeah, good. Nice. Thoughts on this?
Made sense.
All right, let's do a harder one, which is the last problem in the partial fraction stuff. Then we'll start new things. So this is hard. So I've scaffolded it into pieces for you. So first we want to write 3. Ooh, that's not good. We're going to use our theorem and write this thing as a sum of, this over something, and then something else over something else. So I'll ask you, using our theorem...
There's something here.
There's a bunch of question marks. Okay, so I'll ask you, using the theorem, how do you split x cubed minus 1 into a product of linear and possibly quadratic factors? Just factor this guy.
I'm just trying to think.
Take your time.
Are we just legit factoring?
Yeah, well,
right
factor as far as you can, right? So, well, okay.
I forgot. Oh.
Tell me one root which is obvious.
Is it going to be x squared plus 1?
X squared plus... I don't think so. Well, what number clearly gives 0 if I plug it in for x?
Literally 1. I'm stupid.
Yeah, so 1 is a root, right? So we know we can factor out an x minus 1. So that's one thing. Now all we have to do is figure out what's left after we factor out x minus 1. Right, so there's 2 more roots. So here there's either going to be a product of 2 linear terms or there's going to be a quadratic. So do you remember some time in your life when you've memorized a formula for a difference of 2 cubes like this?
I remember it being presented in a terrible manner. I think Corbin and I told you about it.
Yeah, probably.
I don't remember it though.
Okay, well, we can read
I
arrive it.
recognize that this is a difference of cubes.
Okay, good. So you've either memorized difference of cubes or you can read arrive it. So how do we...
Well,
What?
it was not pots. It began with... No. There was a very simple metaphor. Well, not metaphor. Why am I saying metaphor?
Acronym?
Acronym.
Well, okay, we know it's a quadratic. Let's just figure out what it has to be. We know there's an x squared because it has to be a quadratic, and that has to come with a positive sign because when we distribute this, we have to get an x cubed because there's an x cubed on the left. Now, the only thing that I'm forgetting here are the signs. So we know there's an x and we know there's a 1, right? We just have to figure out which is which. Well, we know the 1 has to come with a plus because when we multiply minus 1 times this, we'd better get minus 1. Right, so the third piece had better be minus 1. Now I'll ask you, what about the x? Is the x a positive or a negative?
So we need x times minus 1 to be equal to negative 1 times x. Oh, that's obvious.
Yeah, you're saying we have to cancel. We don't want any linear term when we FOIL this out because there's no linear term on the left, right? So you're saying this has to cancel this, and the second of those two is a minus x, so this product had better be a plus x. Is that what you're saying?
I do... Yes, that is what I'm saying. I ran through the math in my head and it makes sense.
Good.
Is sensible.
Okay. So
did solve right, etc.
Yeah, so the product of minus 1 and this has to be a plus x, which means this has to be a negative sign here. Is that right?
Correct.
Okay. Good. And we could check that, of course, because this gives us x cubed minus x squared. Oh, did we make a mistake? Let's see. X cubed minus x squared minus x. Oh, this isn't right. Minus x squared plus x plus 1. Oh, I made a mistake, because this had better be plus 1 if we want this. That was my mistake. I gave you the wrong sign for the constant term. We want the product of minus 1 and this thing to be minus 1, so that has to be a plus 1, which reverses the argument that you just told me, because now we want this thing, which gives a plus x, to cancel this thing. So actually it was exactly the opposite of what I said. That was my fault. Okay.
Does that mean I'm looking again. Let me see.
Well, let's check that it works now. So when the x hits everything, we get an x cubed plus an x squared plus an x minus an x squared minus x minus 1. And indeed, now it looks like it works because these guys cancel. Right? Do you agree that that's the right factorization?
Yes.
Okay. Good. So actually that's the best we can do. We cannot factor this term into linear pieces because its roots are complex. So this is as far as we can go, actually. So given that that's the factorization, what sum of two fractions should I write in our partial fractions decomposition?
We should have a over x minus 1 plus is going to be bx plus c over x squared plus x plus 1.
Good. Okay. Now I'll ask you, how do we get a, b, and c?
Well, we're going to multiply a times the jazz below bx plus c and bx plus c times x minus 1.
Okay.
And it's going to be massive.
bx plus c. Yeah, it's a bit of a hassle, but okay. So this, well, I'm just going to compactify it like this. Okay, so what happens when I expand out everything in the top?
I'm just going to run through the math on my paper.
Okay.
Actually, it's easier for me to say it. We're going to have ax squared plus ax plus a.
Ah, shit. My pen's fucking up. There we go. Yeah, so ax squared plus a, and then what?
and then bx squared minus bx plus cx minus c.
Good. All right, so now we get three equations from setting the quadratic pieces on the right equal to 0, because there's no quadratic on the left, linear pieces on the right equal to 0, and constant pieces equal to 3. So I'll ask
A minus c equals 0.
A minus c equals 0. Where's that from?
From the from the constant a and the constant c.
So a minus c is 3, not 0, right?
Oof, I don't know how I mixed that up.
Good.
That is what I intended to say.
Okay, a minus c is 3. Good. What are the others?
The others are, let me see. Well, a minus b plus c equals 0.
Good. A minus b plus c equals 0. And the third one?
A plus b equals 0.
Okay. All right. Now, can you solve those three equations for a, b, and c now?
So I believe we can add up equations 1 and 2. 2 and 3 to see that a plus c equals 0.
Good.
And then adding up, 2a plus c equals 0.
Yeah, you're adding these two. Nice. Okay.
Yes. And then we add our first equation to see that 3a equals 3. And thus a equals 1.
Okay, so a equals 1. What are the others?
If a equals 1, then c equals -2.
Good.
And b equals -1.
Good. Okay. All right, so let's see if that agrees with what past Furco did. So let me hide this for a second. So indeed, that's the right split. A over x minus 1 plus bx plus c over x cubed minus, or x squared plus x plus 1. Then part B of the challenge was find a, b, and c, so that's true. And I found a equals 1, b equals -1, c equals -2, which agrees precisely with what you said. Very nice. Part 3.
So the
What'd you say? Oh my god! How did I write that? Oh my lord. Bad times.
I almost thought it was intentional and in some strange language.
Yeah, I'm gonna pretend that's true. I'm very clever. I'm writing it in ancient Arabic, except rendered in Latin text for some reason. Okay, so we know those things. Now let's do the integral. So here's the integral. I put in our a, b, and c, right? Here's the a, and b and c have a negative sign, so I pulled out the minus. So all I did was do our partial fractions decomposition. How do you do the integral on the right side? I'll ask you step by step. You can handle the first term easily, then for the second term you have to split it in a clever way. So
the first term is log of x minus 1.
Good. What do I do in the second term?
Oh, there's a hint there, but I'm trying not to look at it. I don't know if I should or not.
You do you. If you don't want to look at the hint, just think about why U sub doesn't quite work. If you let U be the bottom, then the D...
Let U be the bottom.
Not interpreted the way you're thinking. If you let U be the bottom, du would give you a 2x plus 1, which is not quite what's in the top. So can you split the top into 2x plus 1, the thing that U should be, and then take the difference and move that to a second term that you'll handle separately?
Should we just do -1 plus 1?
Won't help, but yeah, you could try that. So
I'm just trying to think if there's a way to... Wait, no, never mind.
Yeah, as I said, +1, -1 won't make it look like the du in the top, right? The trick is always to try U sub and then make the top look like the du. But as I said, the du we would get from this is 2x plus 1. So you have to add or subtract in a way that makes the top look like 2x plus 1.
I think we can multiply that by 2 and, well, multiply the top by 2 and put a 1/2 outside.
Yeah, good. So multiply the top by 2 and put a half outside.
Get 2x plus 4.
Okay.
And then we do minus 3 plus 3.
Yeah, good. Okay. So 1/2 times 2x, so the minus 3 is a plus 1, and then the plus 3, 1/2 times plus 3 over the same thing. So is this what you were saying? I put this is the minus 3, right, with the 4, which gave you
Yes.
plus 1. And then x squared plus x plus 1 like this. Good. Okay. Let's go step by step. So the first one is easy. What's this integral give?
That is the, well, half of the log of x squared plus x plus 1.
Right, x squared plus x plus 1. Okay, so that piece is done. We don't have to worry about that. All we have to do is integrate this thing, which since we've done everything else, I'm just going to erase it and say, all right, now we just need to, pulling out that 3, we need 3/2 of integral 1 over x squared plus x plus 1. This is the last piece, and once we've done this, we've solved the problem. So how do I do this guy?
Let's see what we have to add or subtract to factor it. Oh, square it, something, I don't know.
To factor, well, we can't factor the bottom over the reals, because we know this guy has complex roots.
I mean,
Here's a
oh, what does the hint say?
Yeah, the only hope is completing the square, right?
Yeah.
So how do you...
So can we plus x minus x? Or something else?
Yeah, let's try that. So x squared, how does this work? How does it normally work when you complete the square? You add b over 2 quantity
you would add
squared.
Oh, you do?
Yeah, here's... You don't remember the...
There's a method to completing the square?
I told you this. When you were on Wikipedia and said, should I copy the thing from Wikipedia? And I said, no, you don't need to copy it. Just do the method. Here's the method, right? If you have x squared plus bx plus c, you always add and subtract b over 2 quantity squared. So you add it here. Here's b over 2 quantity squared. And then you subtract it. C minus b over 2 quantity squared. Why is that the method? Because then the first part, this thing here, is exactly x minus b over 2 squared. Why is that? Because when you FOIL this out, you get an x squared. You get, plus. You get an x squared, then from the cross terms, you get an x times b over 2, and then another x times b over 2, which gives you the bx. And from the third term, you get a b over 2 squared. And then you're left with the constant c minus b over 2 squared. So you don't memorize it. You just add the thing that you need so that this square would match the cross terms. Do you follow?
Okay. Yes, this makes total sense now that I see it.
Okay.
So we're adding plus and minus 1. I mean 1/2, sorry.
Yeah. Good. So x squared plus x plus a half plus, here's where we subtract it. Okay, so now what does this look like?
It's going to be x plus 1/2 squared? I'm confused.
Wait.
Let me check.
I think we added the wrong thing. Isn't it b over 2 quantity squared we were supposed to do?
B over... Yeah, that makes more sense.
So what should this be?
1/4?
Good. So now what is the next line?
I think. I believe that is also 1/4?
No, what's the second line I'm saying?
Can't.
What's the next step? No, take this and complete the square. So what is it now?
I'm just seeing what I need to... checking my work while I'm doing it. I don't know. I see what I need to do. I just need to think.
You don't have to think hard. So what goes? I mean,
I know.
So I'll do this part for you. So 1 minus a quarter is 3/4.
Yeah.
So what goes here if I want the square to be this?
1/2.
Good. Okay, so that
See
complete.
why?
Do you see why?
Yeah.
Yeah, good, because you get two cross terms, x over 2 and another x over 2. Okay. So now this integral is not so bad because we're left with 3/2 integral 1 over x plus a half squared plus 3/4 dx, and this is looking a lot like arctan because the integral of 1 over, if this were just 1 over x squared plus 1, we'd know it would be arctan. So do you see how to make a U sub and do some algebra so that this thing turns into arctan as an integral?
Multiply the outside by 3/4 and the inside by 4/3, and wait. That doesn't seem quite right with that idea.
Well, let's first do a U sub because we want.
Yeah, that would not work. Sorry.
We want this to
I don't know.
look like 1 over u squared plus 1. So what's the
Yeah.
first step?
First potential U sub is letting u equal x plus 1/2.
Yeah. So that's let's do one more step to try to make the whole denominator look like that. So if we wanted to make x plus a half squared plus 3/4 look like u squared plus 1. That would almost work if we let u be x plus a half, but then we'll have u squared plus 3/4, which isn't quite what we want. So I think we should do first the thing that.
Wait, why are you dividing by 3 over u?
That's a 4.
Oh.
This is the denominator here that we're trying to make look like u squared plus 1, right?
Yeah.
Okay. So if we let u be x plus a half, well, we could do that. Fine. Let's just do it in 2 steps. So 3/2 integral 1 over, so u squared plus 3/4. I was trying to do it all in one step, but let's just do it like this. So du is the same as dx, so we've got this. Now, what do I do to make this guy look like a u squared plus 1 downstairs? You were suggesting.
I think I see what you're trying to indicate before. I don't know exactly what it was.
Well, you were suggesting something about multiplying top and bottom to make this guy look like a 1. So how do I do that?
I believe you want to multiply the bottom by 4/3.
Yeah, so you have to multiply the top as well, right?
Yeah.
3/2 integral. So 4/3 all over, so now there's a 4/3 u squared plus 1 du. Now we have to do one more sub. I'm going to pull out the 4/3. This is going to cancel nicely, of course. So can you define a v as a function of u so that this thing turns into v squared in the bottom?
Yeah, v equals 4/3 u.
2 over root 3,
But,
right?
yeah, that makes more sense.
Yeah.
Because it's getting squared to that.
Good. So dv is 2 over root 3 du, and now I'm going to start working up instead of down. Good, so what do we got? Out front, this 3's cancel, so we're left with 2 times, now the du is, I think, root 3 over 2, right, when I solve this dv for du. So du is root 3 over 2, then I get an integral 1 over v squared plus 1 dv. All right, so now what's this?
That is, I think, arctan u? Or, pardon me, arctan v?
Yeah, so we
Oh,
got
2 times. Yeah, root 3 arctan u, where I keep saying u instead of v, but v equals 2 over root 3 u.
good. So this is 2 over root 3u. And then the last step is to put back in u in terms of x. So what was u in terms of x again?
Was it x squared plus x plus what?
No, I think
No.
u was just x plus a half, I think, right?
Yeah.
Yeah, so 2 over root 3, x plus a half. Good. Now, that was the third term, so I've already forgotten what the first two were, so I'm just going to go remind myself with the solution. So
Log of...
yeah.
Well, it was 2 logs.
Yes.
Log of x minus 1 and that stuff, yeah.
So there's a log of x minus 1, there was a half log of x squared plus x plus 1. Remember, there's a minus sign in the previous slide from this thing in the partial fractions. So there's a
Yeah, the first two are basically trivial.
Yeah, good. And then the third one was the only interesting one, and indeed it's precisely what we just said it was. This guy is minus a root 3 arctan 2 over root 3x plus a half. Nice. So, I mean, this, I don't know, it's a long process, but I think this is a very amusing integral in the sense that the left side looks not so bad. It's just 3 over a cubic, and on the right side you get a bunch of logs and arctans. So, I don't know.
Because somehow they're related.
They're related by taking areas.
My screen went black because I've been sitting on it, well, watching it too long, but not actually moving my mouse.
Your screen went black because you put your ass on it.
Whoa, that is...
I've been sitting on it.
Yep, totally.
Okay. All right. So that's the last thing before I introduce the next chapter. So thoughts or questions on this example?
I have no further thoughts or questions.
Okay. All right. So we are done.
What's applications like?
Do you say that in a sense of eagerness because you're sick of integration techniques?
Is it gonna be like integration B, but both prolonged and easier?
I mean, applications are going to be more about seeing which results we can prove or derive using integrals. So some of the integrals will be quite easy, actually, but it's really about what they mean. So, well, I'll preface this. We're going to go through, once we start the next chapter 6 properly, we're going to do this much more carefully, but I'd like to give you a flavor and a preview of the sort of things that we can compute by applying integrals in this little conclusion of today's meeting. So first, I'll give a nice concrete example. So the moral of this story is going to be that integrals solve more general problems than just areas under curves. So I'd like to show you that we can use an integral to prove some formula you may have memorized in geometry class, for instance, for the volume of a pyramid. So we're going to do the following. Suppose you have a pyramid with height, I'll put in some specific numbers, height 5, and the base is a square whose side length is 4. And I'm going to put in an x-axis where, x equals 0 here goes down to x equals 5, the height of this thing. Now we're going to run through, first I'll run through this argument slowly and carefully to convince you that it's a valid proof, but then later, once we've seen the argument a couple times, we'll be much more sketchy. But we're going to try to do the same sort of thing with partitions that we did for finding the area under a curve, but now for this volume. So first let me show you a formula, and then I'll come back to this slide with the picture. Here's what we're going to do. As with partitioning in a regular integral, we're going to partition that x-axis, the height, and call those points in the partition x0 up to xn. Then we're going to construct a lower and an upper sum for the volume of the pyramid by adding up some areas times these lengths in the partition. So let me show you what those things mean visually. So here's an example of the partition. So x0 is the top, then x1, x2, x3, x4. This is not a very fine partition. There's only 6 points in it. Okay. Now, I want to convince you that we can first get a lower bound for the true area of the pyramid. Here's the lower bound. On each partition, use the area of the cross-section at the top of the partition, and then multiply that by the length of the partition. So here at this part, the contribution would be the area at the top. So area of x0 is 0 because there's no area at the top. It's just a point. So you would take the 0 times x1 minus x0. So that's the first part. The second part we're going to add up is the area of x1. So area at x1, the cross-sectional area at the top guy, times x2 minus x1. So you can see that that volume that we get, which is shaded here in blue, that area that we get, volume that we get by taking the area at the top times the height of this partition is strictly smaller than the true area of the pyramid in that region, right? Because if we always take the cross-sectional area at the top endpoint and multiply it by the width of that piece of the partition, you see we always get a figure which is strictly contained inside the pyramid, right? This guy is smaller than the true part of the pyramid in that part of the partition, right? So we keep doing that and add up all of those pieces. So for instance, again, this guy would be the area at the top, area at x3, times x4 minus x3, and that thing gives me the area, or the volume of this little rectangular prism here, which is smaller than that part of the area of the pyramid. Okay, so are you happy that if we do this procedure where we get all of these areas at the top and multiply them, that we'll get some number at the end which is strictly smaller than the true volume? Is that clear?
Yes, it is exceedingly clear.
Good. Okay, I want to make sure every point is painfully obvious the first time. Okay, so that's what I've written with this lower sum. We get a lower sum where at each I, you take the area at the beginning, multiply by the width, and that will be strictly less than the volume. Now you can imagine doing the same thing with these lower endpoints. So for instance, if we always use x1, if we always use the cross-sectional area at the end, this guy is bigger. Again, this guy is bigger. And if you always use these lower face as the cross-sectional area and add those up, you will get something which strictly contains the pyramid because it's always bigger, and therefore it will be larger than the true volume. So in formulas, that's just saying if you add up from I equals 0 to n minus 1, but you always use the area of the cross-section evaluated at the lower point, x sub I plus 1, you will get an upper sum which is greater than the true volume. Okay, is that all clear?
Yes.
Good. Okay, but we've worked with these upper sums and lower sums before, and we've proved things about them, in particular that as you take the distance between points in your partition to 0, the upper and lower sum both converge to the integral. So in other words, if we have the inequality that this lower sum is less than volume to the upper sum, and then we take basically some limit as all of the delta x's, the differences between these points, go to 0, we proved that the lower and upper sums both converge to the integral. So if this volume is trapped between two lower and upper sums, and I take a limit, and the left and right converge to some value, it must be that the volume, well, I'm not going to write it as a limit, I'll write it as an integral, the volume converges to the integral of this function a of x between, in this case, 0 and 5, the height of the pyramid. So we've actually proven that in this case we can compute the volume by partitioning up the height and integrating the cross-sectional area. It's kind of intuitive, right? If you take each area and multiply it by a very small change in the height, you get a volume of a little piece, and you add up all the volume of those little pieces, and you get the whole volume of the pyramid. This was a proof. Okay, questions on that, or is that clear?
No, I have no questions. It is clear.
Okay, so let's actually calculate it this time so we can say what the volume is in this case. So For this problem, we said that the height is 5, and the square base has side length 4. So we can find the cross-sectional area at any particular height. So for instance, I mean, if we know the side length is, 4 at the bottom and 0 at the top, we know that all of these are similar. All of these squares are similar, so the cross-sectional length of one of these squares at one part along x, it varies linearly from 0 up to 5, right? 0 to 4. So if this cross-sectional length, I don't know what to call it, L of x varies...
Mind if I interrupt real quick?
Yeah, sure.
I think this... how do I word this? Integrals seem to be overkill for this problem when you could just find 1/6 of a cube with double the height and the same width.
Yes, that's totally true. You could do that.
But this is a demonstration, so I'll let you continue.
Yes. Good. Okay, so indeed, if we want to find the cross-sectional area at each of these, it's very easy. The cross-sectional length, you just say, okay, well, it's 4 down here, it's 0 up here. It's linearly increasing from 0 to 4 as I go down. So what linear function, L is some slope times x, which is 0 at the bottom, and it's 4 when x equals 5. Well, it's pretty clear that we need this to be 4/5. It's the only linear function which is 0 at 0 and gives you 4 at 5. So that's the length of each of these sides. So the area of a cross-section is 4/5 squared. So the area as a function of x is 16/25 x squared. And as we argued before, the lower and upper sums converge to the integral. So all we have to do is integrate 16/25 x squared from 0 to 5, the height. And by the power rule, of course, we just add 1 and divide by 3. So 25 times the 3 is a 75. And you can plug in 5 and 0. 5 cubed is 125, and simplify 16 times 125 over 75, which gives us this thing. So that is a proof of the form, well, in this case, when the particular values of 4 and 5, we've derived the volume of the pyramid. And as you can see pretty clearly, there's nothing special about the height being 5 and the side length being 4. You can, of course, generalize this and make the following theorem. So the theorem is that for any pyramid with an area base b and height h, the volume will be a third base times height. Why is that true? Well, you run the same argument. Partition the height from 0 to h. Use the similarity argument. Each cross-section is similar to the base. So at a distance x, the fraction between x and the total height h has to be the same as the area at that point x to the area at the largest one, at area h. And that means that this ratio is area of x over b, because we've assumed the base area is b. So you can solve that to get area of x, just multiplying by b, is b over h squared times x squared. Right, I just multiply both sides by b and squared out this thing. But then it's very easy to integrate that function. If you integrate from 0 to h, well, you're going to get an x squared, which you integrate to get an x cubed over 3. Then you plug in an h, and you get an h cubed, which kills the h squared and leaves 1h. And therefore, we've proven the formula for the volume of a pyramid. It's a third base times height. Simple integral with just power rule. Okay, questions on that?
No questions.
Very good. Okay, we're almost done. We started like 20 minutes late because of the logistics, but I'll wrap up shortly. Good. So I'll ask you as a challenge, let's derive the formula for the volume of a sphere. So do you see how to generalize that argument, where now we're going to slice at some distance, maybe z, from the equator. So let's instead of this, we're going to do an integral from minus r. It's radius r. So here's the z-axis. We'd like to do an integral from z equals minus r to z equals r of the cross-sectional area A as a function of z dz. So can you walk me through how would I set up this integral to find the volume of a sphere?
I think just for the sake of simplicity, we can see that this is rewritable as 2 the integral 0 to r of az dz.
Good. Symmetry. 0 to r. Good. Then what?
Let's see. Let's see. The question to ask is, what is az?
Yeah, so what's the area of one of these cross sections? Well, first, what's the formula for the area of this shape?
It is going to be the area of a circle where, let's see, x equals the square root of r squared minus z squared.
Good. So the cross section is a circle of radius labeled here x, and by Pythagoras, that radius x is root r squared minus z squared. Pi times this squared, right? So pi times this radius squared is a of z. So plugging that in for a of z, what do I get?
Sorry, what was the question?
What next line should I write?
Let's see. So it's going to be, yeah, pi radius squared minus z radius squared. Pardon me. Pi radius squared minus pi z squared.
R squared.
Or just pull out a pi.
Yeah.
Yeah.
Okay. Now, being careful about what's a variable and what's a constant, what is the value of this integral?
I believe it is going to be r squared z minus z to the third over 3.
Good. R squared z minus z cubed over 3, evaluated from 0 to r. Okay, so as I erase, think about, clearly the 0 gives us nothing, so all we have to do is evaluate this at the top endpoint, and then what does that give us at the top?
Thus we have r cubed minus 1/3 r cubed,
Third
or 2/3 radius cubed. Oh boy.
And then what's that? 4/3 pi r cubed, which you may have memorized is the volume of a sphere of radius r. Good.
Audible grin.
Log smile. Yes. So just saying it again, I'm going to make this argument about the partition one more time, but then after that I'll stop saying it. So the reason this works is because if we partition the interval from minus r to r, maybe from, call them t, and if we add up all of the infimum of the function f times pi r squared, this whole thing here is the area. Or less, sorry, this thing is less than the area, because infimum. And this thing is greater than the area, because m is the supremum. M, A. So the claim is...
Am I going to get a DC about cones soon?
We've actually already done the cone case, because a cone is a special case of a pyramid, where the cross-section is a circle. So that's done. But good. So anyway, as I was saying, the reason this is a proof is because the true volume of the sphere is strictly bounded between these two lower and upper sums, which we know, since this function is integrable, we've proved it's integrable because it's continuous. This thing converges to the integral, which means the volume is exactly equal to that integral after taking the superinf, and that reduces it to a trivial power rule calculation, which you just told me about. You do this and then get a 4/3 pi r cubed. Beautiful. Okay, so these are some nice results. I'll just flash a couple other things for you quickly. So fairly obvious generalizations. You could do the same thing for a cylinder. What?
Is this even... Alright, integrals are not necessary here.
Yeah, they are. I mean, you don't know what the volume of a cylinder is if you just memorize the formula. You never proved it, right?
It's... Okay, I'm going to concede. I basically, based off of the definition of three-dimensional units, you can break it into h equals 1 slabs.
H equals... I don't know what you're talking about.
That's dogs going crazy, of course. Give me a sec to pause. I'm not going to be able to get them to... God, why?
Yeah, I'm not sure what you said about the definition of
Just
three-dimensional.
go on. I'll bring it up later when they stop barking.
Okay, well, anyway, so yeah, we can't prove this without using either calculus or some clever arguments. I don't see any way to argue that we break this up into H one-dimensional slabs or something, because I don't know what those words mean. But I do know the following argument, that if we run the same thing about partitioning the height, and then argue that the volume is bounded between lower and upper sums, that this thing has to be the integral from 0 to h of the area function, but the area function is constant. Area as a function of x is always pi times the radius squared, where this thing is r. So the integral of a constant function is pretty easy. It's just that constant value times the length of this interval, which is pi r squared h. So this is a proof, quote-unquote proof. I'll explain why I say quote-unquote in a moment. This is a proof that the volume of a cylinder is pi r squared h. Okay, so you could probably see that this generalizes quite nicely. So as we go on, we'll find the volumes of more and more complex looking regions. And I'm not going to repeat this argument about partitions because it goes through pretty much without change. And we'll just use without comment that the volume of such an object is the integral from, say, 0 to h, or here from a to b, of the cross-sectional area of the shape dx. So here's an example of a so-called solid of revolution. So what you can imagine is taking a curve, some curve, I don't know, f of x or something, which is just some one-dimensional object, and then imagine taking the area under that curve, which is two-dimensional, and rotate that area around the x-axis. That creates some volume, and we can compute its volume with an integral. So I want to hop over to a video, because I think this is kind of cute, but these, here we're rotating, say, a cube and, you know, some triangular prism or something, so clearly even before rotating, all of these figures had volume, but imagine, just for the sake of the demonstration, that before moving it, each of these objects was just flat, right? If each of these was just a flat two-dimensional object with area, which is what it looks like when we're staring at it, but of course they're secretly volumes. But if you imagine that this was just a square and not a cube, or this was just a triangle and not a triangular prism, then when you rotate them about the z-axis, those two-dimensional objects would cut out a volume in three-dimensional space. So these are so-called solids of revolution that we'll be able to compute using integration. Good, so that will be something that we do more carefully in the next chapter. But just to conclude, I want to make one comment that we're going to have to do some groundwork before doing that calculation, because we haven't even said carefully what length, area, and volume are. Right? We've been using without proof certain statements like, I don't know, the area of a circle is pi r squared or something, or the length of, I don't know, an arc of a circle, like the length of the circumference is 2 pi r. You can ask the question, what do those words mean? So what does it mean to say that a circle has circumference 2 pi r, or area pi r squared? In a previous meeting, I gave, you know, the school definition of area, which is to say that, well, area pi r squared means you could fit pi r squared of these unit squares of length 1 inside the circle. But those words don't even make any sense. What does it mean to fit pi squares into this region? I mean, that's not an integer. I don't even know what it means to take that number of squares into this region. And if you say, well, you cut one of those squares and then that fits in, well, how do you cut it? And how do you know that it can be rearranged into this region? It's not a precise definition of area. And likewise, we haven't defined volume, and we haven't even defined length. So in the next couple, I think 2 meetings or so, first we're going to very precisely define the length of a curve, right? We know the length of a straight line, you know, we can define this as b minus a, for instance, length. If this is a curve L, we can define length L as b minus a if it's a straight line. But how do you define the length of a curve, right? What is the length of this? It says no clear definition yet. What is the area of some bounded region? Well, You might think that it's related to the integral because that's what we've been saying about areas under curves, but I mean, we've defined what we mean by a partition, and therefore we've defined the number precisely you get by computing an integral, but we've never defined a geometric quantity that corresponds to. So we'll carefully define length next, which we'll use an integral. Then I'll give you this definition of the so-called Jordan measure, which will precisely define areas and volumes in any n-dimensional space. And then we'll go on to compute some volumes of figures using calculus. That's where we're headed. Okay.